So remember, the gradient is saying how this function is changing as with each of the inputs, right? So W2 norm squared is a function mapping from R to the D to R. And each of the components corresponds to how the function changes. So we have partial f, partial W1, partial f, partial W2, and so on. So what that means is when we're looking at this gradient here, the way W changes with respect to W1 is just the derivative of W1 squared, which is 2W1, 2, all the way to 2WD. So you can write this as 2W, right? Okay, so I think something that could be useful to do in the last 10 minutes is just to talk about this expression a bit more. Like we saw it in our math diagnostic, it's in linear regression, and it's something we'll see again later on, just to make sure we fully understand what this quadratic form is doing. Are there any other clarifications or discussions people want to do instead? Okay, let's look at this in more detail because it's a pretty interesting object. So it's called the quadratic form. It's another place it's going to show up later is when we're dealing with multivariate Gaussians. Which means normally when you're dealing with a Gaussian function, you have something that's like e to the minus x squared over 2, and there's some normalizing term. But when you're dealing with multiple dimensional Gaussians, you need to instead use this expression instead. It's called a quadratic form, and what it's doing is you should think of it as a mapping from x, which is, let's say x is in Rn. This function, called f of x, is mapping this x to an element in R. And the way it does that is when you see a matrix expression, generally can be really helpful to write it out in a small case first. So let's do a two-dimensional case. So we have A11, A12, 2-1, A22. I'll post all of these slides in the recording later, so you don't have to worry too much about writing everything down. And the way this converts things into a scalar is it's going to actually, each of the terms in the big A matrix represents how strongly we couple the x1 and the x2 terms. So if you write out this expression, you'll get A11 x1 squared plus A12 x1 x2 plus A21 2 x1 plus A22 squared, x2 squared. So each of these is a scalar term, and in general, we're going to have n squared scalar terms. It's going to be exactly equal to summation aij xi xj, summing over i's and j's. And this is sort of just the generalization of a quadratic function to higher dimensions, right? So one thing you could do right now is, let me add a page. Sorry. You can consider a function like, let's say we have x transpose 4, 0, 0, 1, x. How would you go about visualizing this loss function? So this could be like a linear regression objective. We find that it's 4 in the first dimension on the diagonal and 1 on the second dimension. Is there a potential way we can visualize this, like using the tools we've learned so far?
The equation would look something like 4x x1 squared plus x2 squared.
Yeah, exactly.
So you could try to graph this.
Yeah. So this is actually like the equation of an ellipse that you've probably seen in some other classes before. And what it's saying is that if you set list equal to some quantity, like figure out where it's equal to a certain value, it's going to be exactly corresponding to an ellipse. So we can try to plot this as well. Let's put x1 here and x2 here. And let's consider, like, let's say r equals 4, because that's a nice value. So if r equals 4, then we have x1 equals plus or minus 1, and x2 equals plus or minus 2. And what that corresponds to is x1s are going to be plus or minus 1, x2s are equal to plus or minus 2. So it's going to So the concept of like eigenvectors and eigenvalues is going to come up again later in the course, but in general, what this is doing is it's showing that in one of the directions, the slope is a lot steeper than in other directions. And this is something you should sort of think about when you're thinking about optimization as well, right? Like the size of the step you're allowed to take depends on how steep the direction is. In the direction where the steepness is 4x1 squared, we can only take a smaller step size because if our step size is too big, we're going to overshoot the minimum or potentially start diverging. So there's sort of this implicit trade-off. And more advanced optimizers make this selection by like actually choosing a step size for each of the directions. Okay, so that's how you visualize it. And let's just finally talk about the gradient of this expression again, just to make sure we all understand where that comes from. So in the general case, we have A11, A12, so X transpose and X. So if we're looking at the gradient of this expression, partial f, with respect to, let's say, partial xi, how do we figure out, how do we actually compute it? What terms are affected by xi? Yeah.
Will it only be the diagonal terms that are going to be after the gradient?
Not quite that. It's actually, yeah. The rows and the columns corresponding to the ith entry. So hopefully in your math diagnostic, this is the conclusion you arrived at. So we're going to have this aijth entry, and everything in this row, in the ith row, and then in the ith column. So I guess aii is the only term that shows up in both, right? So in general, what's going to happen is we have a summation in for j not equal to I, we're going to have xi, xj, aij. So this is like all the rows except the entry that shows up twice. We also have j not equal to I, aji. If it's symmetric, these two terms sort of just collapse into one term. And then we also have this aii term itself. Aii. Yeah, there we go. So we want the derivative of this with respect to xi. And if you simplify this expression, you'll eventually arrive at this whole thing collapses down into 2ax in the case where it's symmetric. or A plus A transpose X if it's not symmetric. So one immediate way to use this property is if we go back to this expression here, W2 norm squared, we can write this as W transpose W, right? Can you interpret W transpose W as a quadratic form as well?
Just like A,
Yeah, it's setting A equal to identity, exactly. So it's W transpose I W. So the gradient with respect to W, if we use our answer, is just going to be equal to gradient W. It's going to be 2IW equals 2W. So it's in general just an important concept to keep in mind. Speed up a lot of calculations.